All right, hey everybody, Cameron here. Today we're going to be talking about semiconductors, and semiconductors are super important. They are the principal component of pretty much all of our electronic circuits and devices, whether it's something like a diode or it's the circuit board itself, the microcontroller. Semiconductor theory is at the root of pretty much everything these days. Now, a semiconductor can act as either an insulator or a conductor. And what's the difference between the two? So let's illustrate that now. If we were to connect a battery, a light bulb, and an insulator, something like wood, in this case we have a little twig, we're going to find that that light bulb isn't going to turn on. And this is because charges cannot flow. An insulator impedes the flow of electric current. On the contrary, if we were to use something like metal, aluminum for an example, and connect it in series again with the light bulb in the battery, we're going to find that the light bulb is going to turn on because now current is flowing. So a conductor does not impede the flow of electric current. It allows electricity to flow, and an insulator will impede the flow of electric current. So that's very important. So silicon is the element most commonly used in semiconductor manufacturing. And let's take a look at its properties closely, because we know that it can act as either an insulator or a conductor depending on what the circumstances are. Now we know silicon can form 4 covalent bonds with its neighboring silicon atoms at very low temperatures, like 0 degrees Kelvin. It's really cold. And all of those electrons are actually tied up in their covalent bonds. They cannot move. And so, the semiconductor cannot conduct electric current. When the temperature rises, if the sun comes out, then we're going to have a process called thermal generation. This means that there's enough energy to break some of those covalent bonds, and it releases an electron from the bond, meaning that this electron is now free to travel through the lattice and conduct electric current. It leaves in its place an area of net positive charge, called a hole. And a hole can also move through the lattice. As it is an area of net positive charge, it can attract electrons from neighboring atoms. So an electron from a neighboring atom can actually jump into that hole and leave in its place an area of net positive charge. And what we actually see is a hole moving across the lattice. Now, all of this is great. However, there's a couple of drawbacks. One is that we see the conductivity of the semiconductor is now proportional to the temperature. So if it's very cold and our snowman wants to have a light on, that semiconductor may actually not conduct any appreciable current. And conversely, if it's super warm, there may be too much. So how do we mitigate this? It's with a process called doping. And doping, as you might know, is when you inject a foreign substance to improve performance. So in semiconductor doping, there are 2 types. There is P-type and there is N-type. So what are the differences between P and N-type semiconductors? And more importantly, why are we doing this? So we are doping because we want to increase the conductivity of the semiconductor. We want it to be able to conduct more current than it normally would be able to do. In P-type semiconductors, this is accomplished by incorporating an element from group 3 of the periodic table, commonly boron. And boron has 3 valence electrons. So it can only form 3 covalent bonds with 3 neighboring silicon atoms. And where the 4th bond normally would be, we now have a hole. And as we know, holes increase the conductivity of the semiconductor because electrons from neighboring silicon atoms can be attracted to it, and thus we see the movement of the hole through the lattice, or the movement of current. Now, in an N-type semiconductor, we want to introduce an element from group 5 of the periodic table, like phosphorus. This means it has 5 valence electrons, 4 of which are taken up in bonds with neighboring silicon atoms, and the 5th valence electron is now a free electron and is free to conduct current and move throughout the lattice, thus increasing the conductivity of the semiconductor. Okay? So That's it for this video. I'll see you guys in the next one. Thank you very much.